Hello class, today we will discuss on the following objectives. The first objective would be to calculate the values of the principal normal stresses. So what are the principal normal stresses? The principal normal stresses are those values of the stresses on which only the normal stresses acts and no values of the stresses acts on those particular planes. So if we are using a 3 by 3 matrix, we are working in a three-dimensional space, we will have three values of the principal normal stress, and these are denoted by sigma 1, sigma 2 and sigma 3. Next we will move to the stress invariants. These are the invariants represented by I1, I2 and I3, and these values of I1, I2 and I3 remains constant even if we change our coordinate systems, as we are interested in finding the stress at a point and a number of planes can pass through it. So we can have n numbers of formulations to calculate the values of the normal stresses and the shearing stress. Whatever the coordinate axis we choose, the values of the stress invariance, which is represented by I1, I2 and I3, will always remain constant. Now let us derive an equations to calculate the values of the principal normal stress in a three-dimensional space. So let us consider an oblique plane. This oblique plane is represented by the triangle A, B and C. So this is a triangle having a very small area. That very small area is represented by dA. It is subjected to different values of the stresses, the normal stresses and the shearing stresses at this particular plane. That plane is represented by O, B and C. This plane is subjected to one values of the normal stress, which is given by sigma xx, and two other values of the shearing stresses represented by tau xy and tau xz. The other face, which is represented by triangle O, A and B, this particular phase is represented by other sets of the values of the stresses. The first stress is the normal stress, which is represented by sigma zz. The other two values of the shearing stresses that are acting on this particular plane is tau xz and tau yz. The next phase is the phase represented by the triangle O, C and A. So this one is the triangle, and this phase is subjected to one values of the normal stress, which is represented by sigma yy, and two other values of the shearing stresses that are tau yz and tau xy. So we are interested in this case to calculate the values of the principal normal stresses. In this particular case, the directions, the values of the normal stresses on that is acting on the principal planes. That principal plane is represented by the triangle A, B and C. This means that on this particular plane only the values of the normal stresses acts and no values of the shearing stress acts on this particular plane. In such a case, the directions of the unit vector of this particular plane will align in the directions of the normal stress to this particular plane. So here it is written like that, the principal normal planes. So what are the principal normal planes? Here that plane is represented by the triangle A, B and C. So this triangle represents the principal normal planes on which no shearing stresses acts. So on this particular plane, the plane represented by the triangle ABC, only the values of the normal stresses is acting and no values of the shearing stresses are acting on this plane. In such a case, the normal stress will align in the directions of the unit normal vector n to the principal plane. So in such a case, the directions of the unit vectors of this particular plane, that particular plane is represented by the triangle A, B and C. In such a case, the directions of the normal vector to this plane will align in the directions of the unit vector of this particular plane. So that the unit vector of that plane is represented by n is equal to L I cap plus M j cap plus N a cap. Again, what we have done in the last sections regarding calculating the equations of the equilibrium, we will do the same thing. First of all, we will find a relationship between the triangle ABC with respect to the different triangles we have. This is the triangle, first triangle ABC, its relationship between the triangle OCA. Again, the relationship between the triangle A, B and C with the triangle BOA. Next, we will find the relationship between the triangle A, B, C, this triangle, and the relationship between the triangle represented by O, B and C. So correspondingly we will have three equations or three relationships between the triangle ABC and its projections on the different planes. So the first relationship we can have, dA is the small elemental area of OBC is equal to direction cosine L multiplied by the elemental area dA of the triangle ABC. The second area we can have, the small elemental area dA OAC is equal to the direction cosine associated with it M multiplied by the small elemental area dA ABC. The third relationship we can have, the small elemental area dA represented by the triangle OAB is equal to the direction cosine associated with it n multiplied by the small elemental area A, B and C. Now we know the three relationship between the this triangle, the triangle represented by the oblique plane ABC and its projections on the three different planes. The planes are represented by the XY plane, XZ XZ plane and YZ planes. So now we have a coordinates. We have a coordinates on the plane ABC. That coordinate is represented by the coordinates x, y and z. So the projections of the principal stress vector sigma n, which is represented by this arrow along the coordinates ABC, are given by sigma n is equal to sigma n multiplied by direction cosine L multiplied by the unit vector I cap plus sigma n multiplied by m into j cap plus sigma n multiplied by n into k cap. This is the similar thing what we have derived in the previous lecture. The same formulations would be used, only in this case the thing is that in this case the directions of the unit vectors is aligned in the directions of the principal normal stress, whereas in the previous case it was not a case. There was an angle between the unit vectors and the directions of the normal stress on that particular planes, but over here what we have taken, the directions of the normal stress, principal normal stresses is aligned in the directions of the unit vectors of this particular plane. That plane is AB and C. The next step would be to write the equations of the equilibrium in the x directions, write the equations of the equilibrium in y directions, and write the equations of the equilibrium in z directions, and we can use the relationship. What relation? Which relationship? These are the relationship between the different areas, the projections of the different areas. So we can write the equations in x directions and we can write the equations in y directions in the terms of the forces. So for writing the equations in terms of the forces, what we need to do is to multiply the values of the corresponding stresses on each faces with the small elemental area dA, which is the small elemental area on ABC. Similarly, Then we have calculated the values of the force, and now we can write the equations of the equilibrium. Similarly, over here the values are substituted corresponding to the various projected areas. Similar to this, over here also the values are substituted, but we have find out the relationship between the elemental area ABC and its projections on the different surfaces. Similar to this, we have substituted the values of elemental area ABC over here with the relationship between the projections to its different faces. In the similar manner, we will write the equations in y directions, and we will write the equations in z directions. When we have written the equations in three corresponding directions, x direction, y direction and the z direction, we can see that over here all these constants dA, ABC are everywhere. In all these equations we can find the small elemental area ABC. So what we can do, we can eliminate this. We can eliminate the value dA, a small elemental area ABC, from all these three equations, and then we will be left with the modified values of the three equations, that are the equilibrium equations in x directions, y directions and z directions. So these are the three equations that we have got from the previously formulated three equations. These are the modified three equations. This is the equations of the equilibrium in x directions. This one is the equilibrium equations in y directions, and this one is the equilibrium equations in z direction. So these are the three equations are the linear homogeneous equations, since all the three directions cosines are not b0. So the values of the direction cosines, we know the properties of the direction cosines as L square plus m square plus n square is equal to 1, or we can say cos square alpha plus cos square beta plus cos square gamma is equal to 1. The systems of the linear homogeneous equations has a non-trivial solution if and only if the dependence of the coefficients L, m and n vanishes. Thus we can have this forms of the equations. Again, we have removed these coefficients L, M and N, as these are present in all the three equations. This L, M and N, again this L, M and N. Over here we can write it like this entire matrix multiplied by the coefficients L, M and N, which is equal to 0. Now this is the same equations what we have earlier studied. It is in terms of A minus lambda I. So again, to find out the values of the principal stresses, we will get the cubic equations if A is a 3 by 3 matrix. Over here we have assumed a three-dimensional space, so A will be a 3 by 3 matrix and I is an identity matrix. So this will be an equations, a cubic equations in terms of the lambda, but over here it will be in the forms of sigma n. So we will get three values of sigma from these equation. If we turns the determinant of this equal to 0, it will get a cubic equations in sigma n. So let's see what types of the equations we will get. Now, so the expansion of that determinant which we have derived in the previous slide will give us like sigma n to the power 3 multiplied by I1 sigma n whole square plus I2 sigma n minus I3 is equal to 0. So over here it is a cubic equations with order of 3. This means that this equations will give three values of sigma n. Those three values of the sigma n are known as the principal stresses. Three values, the maximum values will be known as the maximum principal stresses, and the minimum values will be known as the minimum principal normal stresses, and the middle value sigma 2 will be the intermediate values. So over here, in order to make this equations compact, it is given three notations. The three notations are I1, I2 and I3. The values of I1 is given by sigma x plus sigma y and sigma z. The values of I2 is given by sigma x multiplied by sigma y plus sigma y multiplied by sigma z plus sigma z multiplied by sigma x minus bracket tau xy whole square plus tau yz whole square plus tau xz whole square. And the values of I3, the values of I3 is given by the determinant of the matrix we have chosen, which are the various stresses values, the normal stresses and the shearing stress values. These three values, the values I1, I2 and I3, are known as the stress invariants. The properties of these stress invariants are that it remains constant whatever the coordinate systems we choose. So at a particular point, a number of planes can pass and we can have different formulations with us. The different values of the normal stress and the shearing stress acting on the particular plane. But the values of these stress invariants, which are I1, I2 and I3, will not depends upon the coordinate systems which we have chosen. It will remain a constant value. This means that if in a particular case we are getting a values of I1 as 20, say the values of I2 is we are getting it as 30, and for the time being say that the values of I3 we are getting as 100 and 1500. See, we are getting a values of 1500. This means that these values of I1, say 20, 30 and 1500 will remain constant whatever the coordinate systems we choose. And if we solve this cubic equations, we will get three values of the stresses, which are the principal normal stresses. First one is represented by sigma 1. Why sigma 1? Sigma 1 is a general notation for the maximum normal principal normal stress, and sigma 2 is a representations of the intermediate principal normal stresses, and sigma 3 is a representations of the minimum principal normal stresses. So if we calculate the values of these values, again we can calculate the direction cosines associated with these principal values by simply substituting in the characteristic equation, which is given by a minus lambda times I. Here I is the sigma n coefficients. Substitute the values of lambda one by one, we can get the values of the direction cosines associated with those principal stresses. So the learning outcomes for this sessions would be: the first case, the principal normal stresses. Over here in this sections, we have calculated the values of the principal normal stresses, and we have derived the expressions how we can calculate the values of the principal normal stresses. So the principal normal stresses are the planes on which the maximum values of the normal stresses acts, and no values of the shearing stresses acts on this particular planes. So in this lectures, what we have studied, in the context of what, when only the principal stress vector acts on the principal plane and is in the directions of the unit normal vector. So the directions of the principal normal vector on any oblique plane is in the directions of the unit vector, whereas in the previous lectures it wasn't the case. Over there we have formulated a generalized expressions when the stress vector is not in the directions of the unit normal vector. Thereafter, we have calculated the values of the stress invariants. The various stress invariants are I1, I2 and I3. These are the stress invariants which remains constant even if we change our coordinate systems. These values will remains the same. Same. If so, if we are calculating the values in terms of the principal stresses, which are sigma 1, sigma 2 and sigma 3, or we are representing in the terms of the general state of stress at a point, which is represented by sigma xx, sigma yy and the sigma zz, in both the cases, if we are calculating the values of the stress invariants such as I1, I2 and I3, in both the cases the values of these stress invariants will remain constant. It will not change on the basis of the coordinate systems we choose. So this is all for this session. We will meet you in the next session. Thank you.